In this lesson we're going to look at water of crystallization. Now, many ionic substances have the tendency to absorb molecules of water into their crystalline lattice. Now, this water is called water of crystallization. Now, water has what we call a polar molecule. Although the total charge on the water molecule is zero, the positive and negative charges tend to be slightly displaced from each other. So there tends to be more negative charge around the oxygen atom and more positive charge around the hydrogen atoms. So if we have a look at the ionic salt lattice, for example, let's take copper sulfate as an example. Now you'll recognise that the copper sulfate contains these beautiful blue rhombic crystals, and well, what is the structure like? Well, it's going to be made from the sulfate group, which is SO4 2-, that's the negative ion, and the positive copper ions. And these negative and positive ions repeat themselves throughout the structure. And what happens is that the water molecule would tend to be attracted to the positive and negative ions. So each copper sulfate group attracts a number of water molecules like this. Now, in the particular case of copper sulfate, for each copper sulfate group in the lattice, there are 5 molecules of water crystallization. So we write this as dot and then 5H2O. Okay, now this water crystallization doesn't actually affect the chemical properties of the salt. Those remain the same, but they're responsible in the case of copper sulfate for giving it this kind of dark blue colour. Now, I'd also like to say that the copper sulfate, when it contains the water of crystallization like this, it's called hydrated copper sulfate. Let's just write hydrated copper sulfate. And if we heat these copper sulfate crystals in a crucible, what will happen is we will drive the water molecules out of the crystalline lattice. Let's do that. So what happens is the water will slowly evaporate, if you heat it gently, from the hydrated copper sulfate. Okay, that's driven out of the crystalline lattice, and as a result the copper sulfate will then change colour. It'll change into a white crystalline substance, which is known as anhydrous. That means without water. Hydrated means with water. Anhydrous copper sulfate. Now, once you've heated the hydrated copper sulfate to produce this anhydrous, white anhydrous copper sulfate, well, if you let the crystals cool again and add water to the structure, a few drops of water, then you'll notice that the copper sulfate reabsorbs the water into its crystalline structure and changes back to this blue colour. Okay, and it becomes hydrated again. Now, I would also like to point out that whereas the correct formula for hydrated copper sulfate, that's the stuff that we're normally familiar with in the laboratory, is CuSO4.5H2O. The formula for anhydrous copper sulfate, that's where the water's been driven out of the structure, is CuSO4. Okay, so that is the formula for anhydrous copper sulfate. Now, to finish off, we're just going to have a look at a typical exam problem on water of crystallization, and it would typically look like this. So we're told we've got some hydrated magnesium sulfate. All right, so we're going to write dot and then XH2O. That's to say, you're told it's hydrated, but you're not told how many water molecules there are present in the crystal, and it's this that we've got to find. That's to say, the number of water molecules of crystallization that are present. So you'd be given information like this. You might be told that the mass of the crucible is, say, 30 grams, that the mass of the crucible plus the hydrated magnesium sulfate is 33.21 grams. and that the mass of the crucible plus the anhydrous magnesium sulfate, that's to say what we're doing is we're heating this. Okay, we're going to heat this hydrated magnesium sulfate, drive the water out of the crystal, and then measure its mass again, and we find that the mass of this is 31.57, and then we're going to use this information to find X. So the first thing we've got to do is find the mass of the hydrated magnesium sulfate. Let's just make a note of that. Well, that's equal to 33.21 minus 30. You have to use this information usually. Minus 30 grams gives us 3.21 grams. And then the mass of the anhydrous magnesium sulfate, that's the magnesium sulfate with the water removed. That gives us 31.57. Subtract 30. 1.57. And then if we subtract this number from this number, we get the mass of the water of crystallization present in the structure, which is equal to 1.64. So what we really want to know now is how many moles of magnesium sulfate there are present to the number of moles of water. And this ratio will always be a whole number. Okay? So we'll take the relative formula mass for magnesium sulfate, okay, using the periodic table, to be 120 grams, and the relative formula mass for water is equal to 18. Okay, and so what we've got to do now is work out the number of moles of magnesium sulfate present. Well, we know that 1 mole magnesium sulfate weighs 120 grams. Then how many moles weighs 1.57? Cross multiply, and that gives us X is equal to 1.57 divided by 120, which is equal to 0.0131. That's the first bit of information we need. So that's the number of moles of magnesium sulfate present. And now the number of moles of water. Well, we know that 1 mole of water weighs 18. How many moles weighs 1.64? Do the same thing again. X will be equal to 1.64 divided by 18, which is equal to 0.0911. Now, we're running out of space here, so I'm going to move over this way a little bit. Okay, we're just keeping those figures there. Now this tells us the number of moles of magnesium sulfate present to the number of moles of water present in the substance. Okay, so what we need to do now is we need to find the whole number ratio, and to do that we choose the smaller of the two numbers, which is 0.0131, and we divide each number by that number. So that gives us the following ratio. So let's just write, we're working out the moles of magnesium sulfate to the number of moles of water. So we have 0.0131 to 0.0911. We divide each number by 0.0131. Let's do that. That gives us 1 to 6.95. 1 to 6.95. Well, most cases in this type of problem, because because these are so-called experimental figures that they'll give you in the exam, you wouldn't expect the answer to be exactly a whole number. You just got to use your head here and round this off to the nearest whole number. So clearly this is 7, and therefore the value of x is 7. So we can write down the formula for hydrated magnesium sulfate as MgSO4 and then 7 H2O. That's the formula that we've been looking for.